Hello, family. Welcome to another session of Maths Fanatics 24/7. Today, we're going to be looking at the question on sequence and series taken from a past paper. Okay, on 4.1, I'm given the sigma notation, alpha, infinity, k equals to 1. Then I have 5, 3 to the power 2 minus k. Right, perfect. Before I even answer the questions, I'll show you how to plan. In mathematics, planning is the most important thing. Okay, so we're going to plan this question. Sharp. So you always write whatever number you have here. So in this case, I have 1. So I have 1, right? These are inputs, né? We call them inputs. Input 1, right? So obviously the number after 1, if I add 1 is 2, and then the number after 2, the natural number after 2 is 3, right? And then let's go up until 4, sharp. So now let's check what are going to be the outputs, né? So we use input-output method, sharp. So we're going to use a calculator, né? And then I just don't need this. Let's say mode. Okay, let's reset our calculator. Equals to sharp. So I'm going to type the function. This is the function, né? This one here. This one is the function. So it's 5, 3 to the power 2 minus k, remember, is the input. Now, the first input is 1. So I'm going to input 1 and see how much I get. It says syntax error. It means I didn't type something proper. Okay, here. So this must be like that, né? Which gives us 15. So the first value is 15. So the first output is 15. Now we need the second output, né? So the second input is 2. So I'm going to input 2 now. So when we input 2, we get 5, right? So we get 5. Now we're going to input 3. Okay, let's input 3. With 3, we get 5 over 3. 5 over 3. Let's input, we're going to input 4 now, right? Okay. But you can end at 3 if you want to, but I'm just doing it up until 4, just for the sake of it, né? So we're going to have 5 over 9, right? We have 5 over 9. Sharp. These are the first 4 terms that we are adding in this series, né? Perfect. And then the other thing you need to ask yourself after doing this is, what kind of a series is this? Right. So there are 2 types of series that are commonly given, né? The first one is geometric. The second one is arithmetic, also known as linear, né? Linear. Okay, perfect. The geometric, you'll see with this, né? Exponent, né? Exponent. Variable. So if your variable, in this case k, is the exponent, then you know you have a geometric number pattern, né? Perfect. And then here you'll see it with this. For example, 3x plus 5, this is linear. 3k minus 4, it's linear. So here, your variable, your letter, né? It's a variable, né? Your letter is a variable. For geometric, your letter is an exponent, né? Perfect. So in this case, we can all conclude that we're having a geometric number pattern, right? Perfect. Remember, for geometric number pattern is defined by Tn equals to a multiplied by r to the power n minus 1, right? Sharp. So to get a, you just get T1, né? And then r is always T2 divided by T1, right? From your plan, you can easily see that Your first term is 15, so your A must be 15, right? And then your second term is 5. So to do R for T2, I'm going to substitute the second term, which is 5, all over the first term, which is 15, right? And then let's see. If you press a calculator here, you should get 1 over 3. Makes sense? And then the last thing you need to know how to get is your N. Your N in this case is infinity. Ne? So is the sum to infinity in this case, because we don't have a number there. But let me just show you a case, what we were going to do if you had a number. Ne? So if I had a number, okay, let me just give you examples here. So let's say I had 50 here. And then here I have k equals to negative, let's say negative 2. Ne? And then here I have t at k, which is the formula, something like this. Ne? So the n, it's always this. It's always top number. So top minus bottom plus 1. Eh? Write this down somewhere. It's very important. So for example, if I had a pattern like this, my n was going to be n equals to, let's see, my top is 50. Then I minus the bottom, which is negative 2, then plus 1, right? And then if I press on a calculator, or I just do a simple algebra here, the answer was going to be 53. So this was going to be sum to 53 terms. But in this case, they gave us an infinity sign. It means it's sum to infinity. And always, when I see that this is geometric and I see this, I know I'll have to use this formula. Sum to infinity is what? It's a over 1 minus r. Ne? And then I know that this series is what? Okay, let's remove the calculator for now. I know that this series is convergent. Ne? It's convergent. Why am I saying convergent? Because my r is in between. What is the value of r again? There, you see it. So if they say give a reason why this is convergent, you're firstly going to write the formula like this. And then you substitute the r. Ne? So this is your reason why we're saying the pattern is converging. So anything outside this boundary, we say it diverges. Ne? It's divergent. Anything in between the boundary, we say it's convergent. Ne? And then convergent geometric number patterns are always going to have sum to infinity. Okay, perfect. Divergent geometric number patterns do not have sum to infinity. Only convergent can have sum to infinity. Awesome. I think our planning is enough. We can now go to answer the questions. They say write down the value of the first two terms. Oh, we already did it on the plan there. So it's 15 and what? And 5. You get your 2 marks. Then here they want us to calculate the sum to infinity. So the sum to infinity is given by this formula, right? Sum to infinity, it's a over 1 minus r, right? And you can get this on your formula sheet. Ne? This is always given in the formula sheet. Now we're going to substitute, right? Remember, a is the first term, which is 15. And then 1 minus my r is 1 over 3. Then we're going to press this on a calculator, right? Let's get our calculator quickly. Okay, I need to erase here so you can be able to see the screen. Awesome. Now we can get our sum to infinity. So we have 15 over 1 minus 1 over 3, which is equals to what? 45 over 2, right? I always prefer to leave my answers in fraction form, ne? For number patterns. I just like to give the exact values, ne? But if you want to, you can always use decimals, 2 decimal places, ne? unless stated otherwise. So this I can see is 22.5. Perfect. But on number patterns, I advise you not to round off. Always use your numbers as original as possible. Awesome. So 4.1 is done. Now we're going to look at 4.2. Okay. So I'm going to clear all drawings. Perfect. So on 4.2, I have sine 30, cos 30. But I know that sine 30 is what? So 4.2. Sine 30 is half, right? If you're not sure, you can always press a calculator. You press sine 30, the calculator will give you half. And then cos 30, it's root 3 over 2, of which you can also get on a calculator. And then we have 3 over 2. And then we have 81 over root 3 over 2. Ne? This is the first term. So this is T1. Then this one is the last term. Ne? You see, they gave us 3 dots. They mean there are more terms in between, but this one is a finite geometric number pattern because they said here that this is a geometric sequence. Ne? It's finite, so it's ending. Ne? Perfect. Sure. So now they want us to remember before we read the question, we plan first, right? So I know that my A is what? It's half. Then remember our R, we get it by dividing term 2 and term 1, which is square root of 3 over 2 divided by half, which is, you can just press this on a calculator if you want to, but we can also do this, which gives us square root of 3, because this 2 will cancel with that 2. Right, so my R is basically, therefore R is square root of 3. Okay, so I have my A, I have my R, right? So now let me read the question. Okay, let me write them here. Ne? So my A is what? It's half. And then my R is square root of 3. Right. Then I'm going to erase here to create space. Okay, I'm going to erase here to create space. Let's see. How can we erase? Okay, let's check. Clear. Okay, eraser. Let's just erase quickly like this. Okay. Sharp. So I have my value of my first term and my last term and my R, right? Awesome. So now we can proceed. So the question says determine the number of terms in the sequence. The number of terms in the sequence. Okay, sure. So to determine the number of terms in the sequence, I know the value of the last term, right? So if I know the value, I can easily get n, which is what the question is asking. I know the value of the last term. So if I know the value, I can easily get n using the formula of the nth term, right? Remember, this is geometric, so Tn is going to be a dot r to the power n minus 1, right? Which is Tn equals to, my a is what? It's half. My r is square root of 3. And then to the power n minus 1, right? Perfect. So in this case, I have 2 unknowns, right? I don't know the value. I don't know the n in the general formula. But the questions are always going to give you either the value and ask you to find the n, or they'll give you the n, which is the position, and ask you to find the value on that position. Perfect. Remember the last term, the position of the last term is the total number of terms in a sequence. Does make sense? So in this case, I'm going to do this. I know the value of the last term is what? It's square root of 81 root 3 over 2 is equals to half. And then I have this, and then I have that, right? Sharp. So what I'm going to do here is this. Remember, I need to solve for that. And that is part of, let me show you something. And then that is part of this. So firstly, I need to isolate this part, right? Sharp. So obviously, I'm going to remove this by dividing. So I'm going to have 81 square root 3 over 2 divided by 1 over 2 equals to square root of 3 to the power of n minus 1, right? And then now we're going to use our calculator quickly. Let's see. So I have 81 square root 3 over 2 divided by 1 over 2. This becomes 81 and then square root 3. Okay, which is square root 3 and then n minus 1, right? So now that part is being isolated. There are many ways to do this when in this case. But the shortcut here is to use, okay, I'll show you, let me show you both ways actually. The first way, obviously 81 is 3 to the power 4. So I'm gonna change 81 to 3 to the power 4, multiply by, right? Square root, remember a square root, there's a hidden 2 here. So inside we have 3 to the power 1. This can be written as 3 to the power 1 over whatever the root is. So the inside exponent goes at the top, the outside root goes at the bottom. So this can be written as 3 to the power half, which becomes, this was also 3 to the power half, n minus 1, right? And then this will become, let's see. This will, okay, let's go here. This will become, remember, if I have the same basis, I can add the exponents, right? So this side, I'm going to have, let's see, it's 4 plus, let me be a little bit lazy here and just use a calculator. So it's 9 over 2, right? So we keep the base and then we write the sum of the exponents. So it's 9 over 2. And then this side I'm going to FOIL, right? Because we have so this we can treat it as a bracket as well. So n times half is 3 to the power half n. Then half multiplied by -1, it's negative half. And then from there, we can drop the basis and just deal with the exponent. So I have 9 over 2 is equals to 1 over 2 n minus 1 over 2. So in this case, we're lucky because the LCD is common on all terms. So I can easily just say 9 equals to n minus 1. Then if I take the one that said I'm going to have 9 plus 1 equals to n. Therefore, n equals to 10. Then your conclusion is going to say there are 10 terms in this sequence. That makes sense. Perfect. I can show you this. You see, this part here was very tedious. I can show you a shortcut of this, which is using the use of logarithms. The use of logarithms. Awesome. So there is a condition that you need before you can use logarithms. You need the base and the exponent to be isolated. So you can't use logs if you still have this. You need to move to divide it that side first so that you can have the base and the exponent. Sharp. So the exponent always becomes the answer. So I'm going to have n minus 1 equals to log. The base is also, remember, this is the base that is the exponent, right? The base is always the base. And then this part becomes here, comes here. So we have that there, right? Then you press this on a calculator, right? Let's see how much it's going to give us. So I have a log. So we need this one, log of square root of 3. Right? I just like to put brackets there. I'm just used to putting brackets. And then here I have 81 square root 3. That gives me 9. Do you see it? That gives me 9. Then I have n minus 1 equals to 9. Therefore, n equals to 10. Then we're done. Then you always need to write the conclusion to say, therefore, there are 10 terms in this sequence. Ladies and gentlemen, please, if you found this video very helpful, hit the subscription button for more content like this and share with family and friends. See you soon. Tango. Okay.